Hello and welcome to the course Introduction to Docker. Data center and computing infrastructure is becoming more complex every day and more essential to the success of businesses. Data center design has shifted away from the traditional large expensive setups on the IT floor space to smaller component-based solutions. From traditional private data centers to public and private clouds, a variety of different options are available to build and run your infrastructure for your IT and software projects. In this course, we will focus on the container-based infrastructure, specifically using Docker. We will witness how software and applications evolved over the last few decades. We will also see how this evolution led to widespread adoption of containerization technologies. I hope you find the information useful and employ it in your projects. At the same time, I would love to know your thoughts about the course and whether you enjoyed the experience. For now, let's get exploring. As you have already seen in the course overview, this course aims to provide you with the knowledge about containerization of applications and cutting-edge tools like Docker, which makes deploying, managing, and scaling these containers at a very high scale very easy and painless. I hope you enjoy the course and find it instrumental in your day-to-day work and practices. See you in the next section, where we will walk through the evolution of software and get familiar with the containerization of applications. In this module, we will focus on containerization technology. We will go over the evolution of computing, software development, and DevOps processes. We will witness how the increase in scale and complexity has led to the popularity of containers and container-related technologies like Docker. It has been some years since Mark Andreessen, the founder of Mosaic and Netscape, coined the phrase, "Software is eating the world." But indeed, it is true today. The idea that every company needs to become a software company is considered almost a cliche. No matter your industry, you are expected to be reimagining your business to make sure you are not the next local taxi company or hotel chain caught completely off guard by your equivalent of Uber or Airbnb. Modern day software consists of ubiquitous mobile apps and websites. Many of these apps and web applications are a critical part of our daily lives. We rely on them from mundane tasks like paying bills, everyday banking, getting in touch with our colleagues and loved ones. Doing business in the 21st century means embracing a world where software quite literally powers everything, from televisions to cars and from social media to banking systems. Let's explore the implications of this advancement by looking at the evolution of computing over the years. Software development has seen a paradigm shift in the last few decades. From the beginning of computing era in the 1960s up to late 1990s, the software was built by relatively small teams. These teams used large monolithic software stacks to build relatively simple and smaller applications which were used by one to a few tens of people. These applications were deployed on a central network server which the users connected via their terminals and used the application. These terminals use proprietary protocols to connect to the central servers. Then, in late 1990s, web started to gain tremendous popularity. The web applications began to grow in size and complexity. We needed few more people in our engineering departments to build these applications. They began using layered stacks and specialized components for different parts of the system. These web applications were deployed on small to mid-sized server farms, and users connected to these applications over the public internet using their web browsers and popular TCP and HTTP protocols. Now comes the current era of ubiquitous connectivity and ever-increasing adoption of mobile computing. To cater to these demands, the modern mobile apps and web applications are reaching global scale and billions of users. These app and web applications are built by larger teams which are geographically distributed. They build those large applications by stitching together a collection of services, APIs, or microservices. These services use a variety of stacks and are independent of each other. The services run on clusters spanning thousands or tens of thousands of servers or nodes. And the consumers use these applications over the cloud and the public internet using their mobile, tablet, and desktop devices. Since software release cycles are an essential part of software development process, it also evolved along with the overall software development paradigm shift. Here again, from the beginning of computing era to the late 1990s, the software release cycles were longer. The software was delivered on physical media like floppy disks and compact disks. New versions of the software was released after months or years and distributed physically to the end consumers. Then, as the web became popular, we shifted to shorter release cycles and speedy deployments on our web farms. You could now build a feature and release it to the web within a few days to a few weeks. The web applications needed to be available to the users 24/7 with least amount of disruption. So our maintenance window for these web applications shrank. And in the current day and age, the release cycles are much shorter. The DevOps processes have been automated, and teams can develop and deploy a new feature or a bug fix within minutes. Continuous integration, continuous delivery, and continuous deployment practices are becoming really popular these days. And these DevOps processes are helping teams build, test, and deploy code faster and more reliably. Some teams and companies have taken these PD deployments to the next level, and they deploy their code several hundred times on any given day. Since the audience is global and they are always connected, we have very limited or zero maintenance windows. This means that ideally our applications need to be up and running without ever going down even for a few seconds. By the way, we have some excellent courses on DevOps practices available. Please do check them out as well. To continue our discussion on the evolution of mobile computing over the years, let's review the modern day scene in software deployment sphere. You can segregate application components into specialized frameworks. Web applications are written in languages like Python, JavaScript, Java, C#, etc. The background workers use Python, Java, Erlang, and so on. Front-end uses preprocessors like less and SAS. Queuing systems use RabbitMQ, ZeroMQ, and so on, which themselves are written in various languages. Furthermore, the deployment targets have also gotten more sophisticated. Once upon a time, the typical stack was just a simple server with our software bits deployed on top of it. But now, the deployment stacks are much more diverse, distributed, loosely coupled, and complex. You can deploy the code into multiple private environments or put it on your private cloud, maybe public or hybrid cloud. These environments run various operating systems or multiple versions of the same operating system. So basically, the software stack is much more complex using different languages and different frameworks, which are in a state of constant improvement and revision. And of course, all this code needs to be deployed in a variety of target hardware and virtual environments that we just discussed. The system starts its journey on a development workstation and then goes through staging, QA, and production environments. This inevitably gives rise to some compatibility challenges. The web application can only run on a certain flavor and version of Linux, and the database can only run on a particular version of another operating system. And this gives rise to the compatibility matrix of doom, which, if you are in the profession of writing and shipping software, you must be well familiar with it in one way or the other. If not, you will get familiar with it in due course of time. We have permutations of all different software components multiplied with all the possible target environments where our code might need to run today or one day. So all of a sudden, we have an exponential amount of complexity to deal with. We need to ensure that every intersection of this matrix somehow works. Tests pass in the same way on every intersection of that matrix. For instance, the tests need to pass in our local dev environment, then in our local integration environment, and then in QA and production environments. And of course, this does not always work as planned. A typical example is when everything is working perfectly okay on our dev workstation with a certain version of Python libraries and certain version of the libc, certain version of the operating system, when the same code is deployed in production environment, it does not work because the Python package or the Ubuntu version did not exactly match the version on our workstation. Such a software-driven world requires solutions that can solve specific problems while reducing capital costs, the time it takes to implement new functionality, and deploy new infrastructure quickly. Modular design techniques and container-based solutions are the answer. Let's explore what these are. Let's come back around to the complexity problem in a software development and deployment scenario. Like most problems, when we look for a solution, it is always better to look at other similar problems already solved by people before us. A very apt analogy for the problem can be drawn using the shipping industry. For centuries, humanity has had to ship stuff all over the world. This stuff came in various sizes, shapes, containers, and characteristics. The shipping industry had to figure out how these goods could be handled. What kind of truck could be used to haul them into the shipyard? What kind of cranes could be used to load them into the ship, etc., etc. The process of shipping our goods was tightly coupled with the goods to be shipped. Each provider of goods and the shipper needed to have specialized personnel and equipment to handle and store the goods. They needed to maintain all the expertise and infrastructure ready to go. So it made for very brittle, expensive, and cumbersome process. Representing this concern in the matrix, we can see that the situation resulted in a similar matrix of compatibility. Possible types of product to be shipped multiplied by the possible mode of transportation or shipping, with an ultimate goal of making goods reach their destination safe and intact. Some 50 years ago, someone had a brilliant idea, a container, called the intermodal container. The shipping industry standardized the size, the weight, shape, dimensions, doors, locks, mechanisms, and identification features for the containers. I'm pretty sure we have all seen a lot of them in our lifetimes. With these standard containers, we can ship anything to any corner of the world. Any size, any shape, you name it. Not only can you ship them conveniently and safely, you can stack them and ship them in a very efficient manner. And all of those different goods can be shipped at the same time. Not only that, the trucks and cranes needed to handle and transport these containers were also standardized, so no special equipment or expertise was required to handle different types of products. Now all of a sudden we have a separation of concerns. So this separation of concerns brought about efficiency and automation, and it ended up changing the world economy because it is so much cheaper and reliable to ship things with containers. So if you are shipping coffee beans, then your only problem is to make sure that coffee beans fit snugly inside a container. You just fill up the container with coffee beans, lock and seal it securely. Then the shipper, using a standard equipment, will be able to take it from your warehouse, ship it, and deliver it to your customer on the other end of the world. You just need to choose a standard shipper who knows how to handle these standardized containers. Therefore, you are not bound to one specialized shipper. Not only that, the future infrastructure providers and shippers can design their equipment based on this agreed upon container, and it will be all compatible. No one will need to rejig their system to handle any type of goods. So it is future proof as well. You can focus on building faster and better infrastructure like better roads, faster ships, more efficient trucks, rather than worrying about the compatibility issues. So we basically went from this chaotic way of shipping products to this more organized, efficient, reliable, and faster way of shipping products. So much so, this new method of shipping goods changed the world economy forever. Today, most cargo around the world is shipped in standard containers. Containers have brought about an enormous cost savings in shipping and logistics cost. Today, 5,000 ships deliver over 200 million containers per year. We can look around the room and we can quickly count the things which will not be in our rooms, our houses, if they were not shipped from other parts of the world. So the container solution solved the shipping problem and solved it really well. Coming back to our original problem, the goal here is to solve our compatibility matrix by moving away from the physical or virtual hardware. We can learn from the shipping analogy and solution and do the same thing for software as well. So just as we moved slowly away from physical servers to virtual servers, we start moving closer to these tiny little software containers which can contain all our code and can deploy it directly to our target environments in the exact same configuration as it ran in our development workstations. Let's take help of another analogy to understand use of containers on software development and deployment. Another analogy which may be relevant to the containers is from the animal world. By the way, I apologize for this gory analogy, especially to our vegetarian friends, but this is a pretty apt one for the complex digital world we live in. Back in the days of physical and even virtual machines, we used to name and care for our servers like we name and care for our pets. We used to monitor them, and when they got sick, we used to take them offline and fix them or reconfigure them. This works when you have a relatively small cluster of few machines to worry about. But when you're dealing with thousands or tens of thousands of machines, this specialized care is impossible. Generally, about 2% of the nodes can fail on any given day, which means we will have to care for and heal a lot of servers on a continuous basis. So using containers, we can treat our nodes or servers like cattle. These are anonymous members of the cluster and are identical to each other. If they experience any issues, we simply sacrifice them, replace them with new ones. Containers are a solution to the problem of how to get software to run reliably when moved from one computing environment to another. This could be from a developer's laptop to a test environment, from a staging environment into production, and perhaps from a physical machine in a data center to a virtual machine in a private or public cloud. Containerized data infrastructure is a step forward in the industry, combining maximum energy savings with operational flexibility. With ubiquitous connectivity and our insatiable desire to connect with the world, software and web applications have become ever more sophisticated. With the world getting faster internet access and mobile connectivity, these applications will only grow larger and more complex. In turn, the infrastructure deployments are getting larger and more complex as well. When we deploy new applications, we need to slice or portion our infrastructure to host the new application. For instance, we need to say for our backend database, we will use a large instance of a virtual machine, and for our web servers, we will use 2 load balanced web servers. Could you imagine if we had to make these type of decisions while running any application on personal computers? Suppose if your operating system asked you which CPU should the computer use to run a browser window every time you ran a browser. Then it asked you where to run the email client. Won't it be terribly annoying? But the modern operating systems are smart enough to figure out how to run and manage individual instances of applications simultaneously. The operating systems have components like schedulers, memory garbage collectors, virtual memory to continuously manage our running applications. What if we had similar operating system to manage and run our data centers as well? Whether we are managing 2 virtual nodes or 10,000 of them, won't it be nice just to instruct our collection of servers or our data center, hey data center, I want to run a web application and a database. Here is the code and here are the commands to run these applications. Please figure out which nodes can run these applications, deploy them, and run them. By the way, if any one of those nodes die, please make sure you move my application to another healthy node so that the end users do not experience any disruption. Containers carry a lot of core benefits to deployment of applications. Containers can help us isolate all our dependencies and deploy them into our target environment in a reliable and consistent manner. Containers are hardware agnostic. The container engines can make sure that we can run our containers on any distribution of Linux or other operating systems as long as they comply with the container APIs. Container operations and deployments can be fully scripted and thus automated. This works really well for DevOps processes. Containers are really lightweight, where virtual machine images could range from 10 to hundreds of gigabytes. Containers are only 10 to a few hundred megabytes. So they occupy less space and are very efficient to handle. Because of their small size, copying and moving them from environment to environment is very efficient. Because of the underlying container technology, containers are very portable. Container images can be deployed on multiple operating systems and hardware configurations. We can deploy many of these isolated units of applications on a single physical or virtual machine. This high density helps us achieve very high efficiency and resource utilization. But how exactly do these containers are of help to software developers and engineers? They build and run their code on their local containers and then ship them to be deployed in any target environment without worrying about any compatibility issues. Containers also take away any chances of other applications polluting the target environment by installing any incompatible version of the library or misconfiguring some global environment variables. Engineers can consistently deploy the exact version of packages which are needed by their code to run. Since containers are highly scriptable, developers can automate all the build, packaging, and deployment tasks, thus making the overall process more reliable, robust, and efficient. Let's look at what containers bring for DevOps engineers. They can configure their runtime environments with container hosts and run anything which has been packaged inside container images. Since everything is standardized, the DevOps engineers can deploy the software consistently and in a repeatable fashion. This automated and repeatable process naturally leads to more efficiency, and small number of DevOps engineers can manage larger and larger infrastructure footprints. Again, because of excellent scripting support, container deployments can be automated. Okay, so far you have had a good overview of containers. Our discussion on containers is incomplete without talking about Docker, the hot container technology which is taking the DevOps world by the storm. Docker is an open source engine that can help you automate the deployment of applications inside software containers. It was released in March 2013 and has been gaining popularity ever since. It has over 100 million downloads and over 75,000 applications are running as Dockerized applications. That's a lot. Large companies like eBay, Rackspace, Spotify, Yelp, etc. are using Docker technology in their production data centers. But Docker is free and easy to use and easy to get started, so even startups are using Docker technology for building innovative products. Most of the startups I work with use Docker to deploy their applications. Docker has become synonymous with container technology because it has been the most successful at popularizing it. Let's refer again to the compatibility metrics we had been talking about. You can now easily and reliably deploy diverse applications built using different frameworks, languages, package versions into many different target environments by simply packaging them up into container images and deploying these container images in the target environments. Docker separates applications from the underlying infrastructure using container technology, just like virtual machines separate the operating systems from the underlying bare metal hardware. These diagrams provide visual clues about the differences between deploying our applications on virtual machines versus deploying them as Dockerized applications. In each scenario, we start with a bare metal hardware server which has a host operating system. In case of virtual machines, we run a hypervisor which is responsible for launching many virtual machines with the guest operating system. This guest operating system is quite heavy, ranging from 10 to few hundred gigabytes. This reduces portability and introduces very tight coupling. On top of this guest operating system, we deploy our application along with our application code, the dependencies, libraries, and packages. In this case, our application relies very heavily on the guest operating system to provide a clean and sanitary environment. But in a containerized application, we do not have a burden of any guest operating system. The operating system is virtualized with the help of the Docker engine. We deploy only our application code, runtime libraries, dependencies, etc. in an isolated environment in container images. Since these containers contain only the required bits, they are only a few megabytes in size and thus very efficient and portable. These containers are then run by the Docker engine. We do not need to worry about the interaction or effects of the operating system. It is outside of the scope of our container. Equipped with the basics about Docker, let's see how to install Docker. Let's walk through the process of installing Docker on your workstation. Installing Docker is actually pretty straightforward, but since Docker is being actively developed, it will be best to refer to the latest version of the installation documentation. The URL for Docker reference documentation is https://docs.docker.com. At this location, you will find the documentation for installing Docker engine on any popular operating systems available. In this demonstration, we are going to be working with Ubuntu Linux. The installation steps to be followed are quite simple. Start by updating your packages by using apt-get. Then add a new repository for Docker packages. Here are the detailed steps for adding the repository. After that, update your apt packages index once again by executing sudo apt-get update. As shown here, you can add apt-get update and purge the old LXC repo as a container engine if it exists. LXC is an old Docker engine. Docker has made significant changes to their engine, so it is necessary to purge these old packages. After updating your apt repositories, you can install it using apt-get install command by executing sudo apt-get install docker engine. So you see that the install process for Docker is a simple and straightforward one. Another package that we need to install is Docker Compose. Just like the Docker installation, the Docker Compose installation process is also very straightforward. Here is a link to the latest document which outlines the Docker Compose installation process. https://docker.com/compose/install. We will discuss Docker Compose in subsequent demos. Now here are some Docker terms and concepts that you should get familiar with before going further in the course. Docker images are templates or the basis of our containers. We can deploy these images to run our container on top of the Docker engine. A container always starts with an image and is an instance of that image. An image is a static specification of what the container should be at runtime, including the application code inside the container and runtime configuration settings. Docker images contain read-only layers, which means that once an image is created, it is never modified. A Docker registry is a searchable catalog or registry application which lets us distribute and find Docker images. A Docker registry is a place where container images are published and stored. A registry can be remote or on premises. It can be public, so everyone can use it, or private, restricted to an organization or set of users. A Docker registry comes with a set of common APIs that allow users to build, publish, search, download, and manage container images. Docker Hub is a cloud-hosted service from Docker that provides registry capabilities for public and private content. Docker Hub is a public cloud-based container registry managed by Docker. Docker Hub provides image discovery, distribution, and collaboration workflow support. In addition, Docker Hub has a set of official images that are certified by Docker. These are images from known software publishers such as Canonical, Red Hat, and MongoDB, etc. You can use these official images as a basis for building your own images or applications. A Docker file is a text document that contains all the commands a user could call on the command line to assemble an image. Developers use Dockerfiles to build container images, which then become the basis of running containers. A Docker file is a text document that contains all the configuration information and commands needed to assemble a container image. With a Docker file, the Docker daemon can automatically build a container image. This process greatly simplifies the step for container creation. Docker container is a standardized unit of software with all the dependencies. Each container is based on a Docker image. Docker Swarm is a clustering and scheduling tool for Docker containers. Swarm can establish and manage a cluster of Docker nodes as a single virtual system. Docker Compose is a tool for defining and running complex applications with Docker. With Compose, you can define multi-container application in a single file, then spin your application up in a single command, which does everything that needs to be done to get it running. Docker daemon, also known as the Docker engine, is a thin layer between the containers and the Linux kernel. The Docker daemon is the persistent runtime environment that manages application containers. Any Docker container can run on any server that is Docker daemon enabled, regardless of the underlying operating system. Let's review the functionality provided by Docker. First, let's execute docker ps command. As you may recall, docker ps command only shows the running containers by default, which is why right now we can see no container is running on our system. When you want to run a container, you will need to have some container images beforehand. Let's inspect what images are available to us on our system. To do this, we will execute docker images command to display all the existing images. And here it lists out the images we have downloaded already. Apart from the images already available, you can also pull more images from the internet. Let us show you how to do this. We are going to try and download something lightweight. There is a lightweight operating system called BusyBox. BusyBox combines tiny versions of many common Unix utilities into a small executable. It provides replacements for most of the utilities you usually find in GNU file utils, shell utils, etc. The utilities in BusyBox generally have fewer options than their full-featured GNU cousins. However, the options that are included provide the expected functionality and behave very much like their GNU counterparts. BusyBox provides a fairly complete environment for any small or embedded system. It is quite a popular image to test out Docker functionality. What we are going to do is that we will execute docker search BusyBox command. What this command does is it goes out to the internet and searches for all the container images which match the name BusyBox. Here is the search result for the images available freely and publicly. We will discuss more about the actual source of these search results later. Okay, so now we have got the BusyBox container image we are looking for. This is the base image released by Docker. There are other images that are customized versions of BusyBox images modified by other developers according to their needs and shared back to the community. So now that we have found the image we are looking for, the next step is to download it on our system. For that, we will use a command called docker pull. Let's execute docker pull BusyBox to download it. So as you can see, it has to download this image from the internet, but since container images are so compact, the process took only a few seconds. Now let's execute docker images command to verify that the new image has been downloaded and it is ready for us. And voila, we can see the BusyBox image is in the list. Let's execute another search, and this time let's search for CentOS. Here you can see the official CentOS image. Since Docker is so popular and people across the world are customizing and sharing images on public repositories, you can simply search the Docker repositories for any particular operating system or package. There is every possibility that you will find something relevant. And if it doesn't exist or doesn't match your exact requirements, you can download the closest match, customize it, and share it back with the community. You can easily look for images for popular packages like Apache, MySQL, Packstack, OpenStack, Tomcat, etc. All these popular packages are readily available in the public Docker repository. Next functionality that we should discuss is the Docker Hub. Docker Hub is a cloud-based registry service. It provides a centralized resource for container image discovery, distribution and change management, user and team collaboration, and workflow automation throughout the development pipeline. All the publicly shared Docker images are actually stored in this public repository. Even the Docker search command we used earlier basically searches Docker Hub repository for available images. The URL for Docker Hub is hub.docker.com. Let's visit Docker Hub and explore it. Alright, so here is Docker Hub. This is the web-based interface to the public repository. Here also you can perform a search for a Docker image. For instance, let's search for BusyBox. You can see it returns familiar search results which were found in the terminal window as well, which proves that the shell docker command performed the search against the same Docker Hub registry. The concept of Docker image repository is not limited to Docker Hub or public repositories only. You are free to set up private repositories or corporate repositories where you can store your private Docker images or share these images only within your own team or department. Not only that, you can configure your Docker search commands to search across your private repositories. Now, let's discuss the Docker run command before we move on to other components. Let's execute Docker images and grep busybox command. We have already verified that busybox is downloaded and available to us. Next, let's try to run this image by using the Docker run command. Docker run can start the process in the container and attach to the console for the process's standard input, output, and standard error. It can even pretend to be a TTY. This is what most command line executables expect, and pass along signals. We will also pass in a few extra parameters to our command. -I for interactive mode and T for enabling terminal session. And finally, we will pass in the image name BusyBox. And just like that, the image is up and running. Now we are inside the BusyBox image container. If you want to exit the container console, you need to press Ctrl P plus Q, and you will be back on the main terminal session. Let's now again execute Docker ps command. We can see that the container is still running. This is the container ID launched using BusyBox image, and an automated name will also be generated by Docker. You can change this name via Docker run command. You can attach to container terminal once again by executing Docker attach D39 command. Whenever you perform operations on the container, remember that it is more than enough to use the first 3 characters of the container ID in our command. BusyBox is a very tiny image, but it is almost a full-featured Linux distribution. So we can execute any of the Linux-based commands in our container. First, let's check the container version by executing uname command, and you can see the version is 3.13.0-71. Now we are going to jump out of the container image and back on our host terminal. If we execute the same uname command again, you will either see that the host machine is using the same kernel version, or the container is using the same kernel as the host machine. So basically, the container has all the capabilities to perform the operations that are performed in a full-fledged Linux distribution. You can see the file system inside our container right here. Whatever changes are made inside the container will be limited to the container itself. These will not affect the host machine at all. You will need to execute the Docker run help to get complete documentation about Docker run command. As you can see, here are the options which we can use with the run command to run our container. Some of these options are controlled on cgroup level. For instance, the blkio weight controls block IO relative weight between 10 and 1000. The cgroup parent controls the optional parent cgroup for the container. CPU period limits the CPU scheduler period, etc. Basically, when a virtual machine is launched inside a KVM, you have to specify the computing capacity like number of virtual CPUs, memory, etc. you want to allocate to the virtual machine. Say we allocate 2 virtual CPUs and 2 gigabytes of RAM. That means our virtual machine cannot consume more resources than what are allotted to it. Moreover, as the cumulative compute capacity on the host machine runs out after launching number of virtual machines, no more VMs could be launched on that host. In effect, the resource allocation of the host machine gets controlled manually. But how do you allocate or control the resource allocation to the containers? You will notice that when we launched containers earlier, we did not specify any CPU or memory limit. This is because Docker automatically manages all that internally. Suppose if there is a high priority container image, you would want to run and allocate extra resources to that container. To do this, you can tweak the exact resource allocation to your containers. Another option is -p for publishing a container's port to the host. Using this option, you just need to mention which port to publish, or you can also provide a host mapping. Say, if you are going to run Apache web server inside a container, you can run it on default port 80, but map it to another port on the host. The mapped host port could be any available free port. For instance, we can map our port 80 from the container to port 1234 on the host. Now, let's try to remove the container. First, you will need to stop your running container using the docker stop command. But in order to do that, we need to get the container ID. So let's execute docker ps once again, and then execute docker stop d39 command, which will stop our running container. If you will execute docker ps command again, it won't display the container in the list, which means the Docker container has actually stopped running, and docker ps displays only the running containers. And with the option -a, docker ps lists all the containers, not just the running ones. If you want to get rid of a container, you will need to use the rm command. Let's execute docker rm d39 command. See how it has removed the container. Furthermore, if you want to remove the container image as well, then you need to execute docker rmi busybox command, and you will see that the image has also been removed. Let's move to the next Docker component, which is Dockerfile. Docker can build images automatically by reading instructions from a Dockerfile. A Dockerfile is a text document that contains all the commands a user could call on the command line to assemble an image. Using Dockerfile, users can create an automated build that executes several command line instructions in succession. Let's have a quick look at an example of Dockerfile. This Dockerfile essentially runs an app which we have written in Python language. We start with a Python 2.7 image. After that, we issue certain commands to Docker, almost like a scripting language which Docker can use to actually build a desired image. We pull a Python 2.7 image. Then we add some code to this by copying over all the files from a current directory into this particular location. We then change the code location by using workdir command and install all the dependencies for our code by running pip install requirements.txt file. Finally, we ask Docker to run the Python app.py application for us. So based on these commands, we set up a Docker container which already has Python 2.7 installed. We deploy our Flask app code into it and then update all the dependencies before finally running the app. And since we are running a Flask application, we need to install Flask as a dependency. Let's verify that by inspecting our requirements.txt file. So here you can see Flask is listed as the first dependency. And we are also installing Redis because our demo app connects to a Redis database. And just to confirm, we list our container images available on this host. And you can see we do in fact have Python 2.7 image available to us. So the process of building our image from our Docker file goes something like this. Docker pulls the required image file. If it's not available locally, then it will pull it from Docker Hub. Then it copies necessary folders and files into the code location within the Docker container. Next, Docker updates the dependencies of the app by running pip install. And finally, Docker launches the app.py file to run the Flask application. As far as our code is concerned, here is the code for our app.py. And you can see this is a very simple app. It connects to a Redis database using this connection information right here. It displays the number of times user has visited this app and stores that number in the Redis database. In other words, it will display the latest hit count for the app. So every time we visit the app, it will increment the hit count and we will get a message which says, "Hello world, I have been seen n times." So that is the simple functionality provided by this app. Apart from the commands used in our sample Docker file, there are a lot of other commands available to us which can be used in Dockerfile. You can visit docs.docker.com to find a complete reference on Dockerfile commands. Okay, after going through our Dockerfile, we have to take the next step, which is to actually build the Docker image using our Dockerfile. So let's execute docker build -t web001. The -t option lets us specify a name or tag for our image. So here web001 is the name of the image, and now it is building the image following all the commands we used in Dockerfile. Let's give it a few seconds. Okay, now our image is ready. Next, let's execute Docker images, and you can see that our newly created image web001 is in the list of available images. The next important component of Docker that we are going to discuss is the Docker Compose. Docker Compose is a tool for defining and running multi-container Docker applications. You can use the Docker Compose file to configure your application services. Then, using a single command, you can create and start all the services from your configuration. The Docker Compose file is a YAML file defining services, networks, and volumes. A service definition contains configuration which will be applied to each container started for that service, much like passing command line parameters to Docker run. Likewise, network and volume definitions are analogous to Docker network create and Docker volume create. Docker Compose is more like Heat template in OpenStack or Amazon CloudFormation. Using Docker Compose is basically a three-step process. You define your app environment with the Docker file so that it can be reproduced anywhere. Then you define the services that make up your app in a file called dockercompose.yml so they can run together in an isolated environment. Lastly, you run Docker Compose up and Compose will start and run your entire app. So we can script our environment and Docker Compose will create the environment for us. For our Flask demo app, we've already created a Docker Compose file. Let's review it now. There are two versions of Docker Compose file format. Version 1, the legacy format, which does not support volumes or networks, and version 2, the most up-to-date. For the purpose of this demo, we are using version 2 format, and it is the one which is more prevalent as well. The first section is the services section. This section lists all the services which you want to run as part of this Docker composition. You can list all the containers that make up each service and any options or parameters you need to pass to the service while setting up the container. In our example, the first service is a web app service which runs on Python Flask app. Since we have named our web image web001, we will update our compose file with the same name, and we map the port from this container to host Let's go with port 5000 being exposed on the same port 5000 on the host. By default, the Python Flask apps run on port 5000. Next, we will attach the volumes to our container. The volumes command mounts paths or named volumes onto our containers. Here we can optionally specify a source path on the host machine. So here we will add the current directory from the host path to the code folder inside our container, and this is essentially to run the python app.py file. The next section is the depends on section. This section helps us express dependencies between the services. So Docker Compose up will start services in the dependency order. In the following example, Redis will be started before the web. So basically we are saying that our web 001 service depends on Redis, and Redis is another service defined in the Docker Compose file. So now we have a Docker Compose file that lets us set up our environment using this file. To run our environment with Docker Compose, all we need to do is to execute Docker Compose up. First, let's execute Docker ps command to verify that currently no container is running. Now, let's execute Docker Compose up command. What's happening in the background is that web 001 image is launched and a Redis container is launched based on the configuration we provided in our Docker Compose file. We do not have to run these containers individually. Docker makes sure that these images are built and containers are launched in proper sequence. Before we conclude this demo, let's verify the status by opening another terminal window. You can see here that there are 2 containers running right now. This is because the example we have been running is a pretty simple one composing of only 2 containers. But Docker Compose can be used to set up quite complex infrastructures as well. Let's quickly review the status of our running containers. The first container is Redis. It runs on port 6379, but this container port is not exposed to the host. We do not need to, since only app needs to connect it from within the container, so we do not need to publish this port. And we have our web 001 image which we built earlier, and this will run the app.py python flask app. We already reviewed the code for this app. It is going to query the Redis database and return the hit count. This image maps the container port 5000 to the host port 5000. Let's execute netstat -tulpn and grep 5000, and you will see a Docker proxy is running at port 5000. So any request which comes from the outside of this host on port 5000 is redirected to web 001 container. Now, if you open the browser and enter our local IP address 10.203.51.25 on port 5000 in the URL address bar and hit enter to open the application, we see that our app is running fine. Every time we refresh or visit the page, the hit count is incremented by 1. That verifies that our Docker containers are working as expected. So this concludes our demo of Docker components and functionalities. And here are some popular Docker commands as well. We have docker start, which starts a container. Stop does the opposite. Docker run creates and starts a container. Docker attach connects to a running container. Docker ps lists running containers. Docker exec executes a command within a running container. Docker images shows all the images available on our system. Docker search searches the registry for a Docker image. Docker pull pulls an image from the registry. From an enterprise perspective, Docker has 3 things working in its favor. It appeals directly to the developers, which means it has closer linkage to business decision makers than some of the other hot trends at the moment. For example, software-defined networking or software-defined storage. It is directly aligned to the concepts of cloud native applications, DevOps, and microservices, which appeal to both development and operations teams that are trying to determine the best ways to build and operate the next generation of applications for cloud, mobile, and big data. It solves some of the cloud portability issues that virtual machines have not solved, which means it will appeal to the leading CIO desires to build a scalable system. Docker image format, extensive APIs for container management, and innovative software distribution mechanism have made it a popular platform for development and operation teams alike. Docker brings notable benefits to an organization. For example, minimum declarative systems, predictable operations, extensive software reuse, and true multi-cloud portability. Docker is already changing the way organizations build systems and deliver services. It's starting to reshape the way we think about software design and the economics of software delivery. That is all for now in this module about containerization of apps. To continue our discussion on the evolution of mobile computing over the years, let's review the modern day scene in software deployment sphere. You can segregate application components into specialized frameworks. Web applications are written in languages like Python, JavaScript, Java, C#, etc. The background workers use Python, Java, Erlang, and so on. Front-end uses preprocessors like less and SAS. Queuing systems use RabbitMQ, ZeroMQ, and so on, which themselves are written in various languages. Furthermore, the deployment targets have also gotten more sophisticated. Once upon a time, the typical stack was just a simple server with our software bits deployed on top of it. But now, the deployment stacks are much more diverse, distributed, loosely coupled, and complex. You can deploy the code into multiple private environments or put it on your private cloud, maybe public or hybrid cloud. These environments run various operating systems or multiple versions of the same operating system. So basically, the software stack is much more complex using different languages and different frameworks, which are in a state of constant improvement and revision. And of course, all this code needs to be deployed in a variety of target hardware and virtual environments that we just discussed. The system starts its journey on a development workstation and then goes through staging, QA, and production environments. This inevitably gives rise to some compatibility challenges. The web application can only run on a certain flavor and version of Linux, and the database can only run on a particular version of another operating system. And this gives rise to the compatibility matrix of doom, which, if you are in the profession of writing and shipping software, you must be well familiar with it in one way or the other. If not, you will get familiar with it in due course of time. We have permutations of all different software components multiplied with all the possible target environments where our code might need to run today or one day. So all of a sudden, we have an exponential amount of complexity to deal with. We need to ensure that every intersection of this matrix somehow works. Tests pass in the same way on every intersection of that matrix. For instance, the tests need to pass in our local dev environment, then in our local integration environment, and then in QA and production environments. And of course, this does not always work as planned. A typical example is when everything is working perfectly okay on our dev workstation with a certain version of Python libraries and certain version of the libc, certain version of the operating system. When the same code is deployed in production environment, it does not work because the Python package or the Ubuntu version did not exactly match the version on our workstation. Such a software-driven world requires solutions that can solve specific problems while reducing capital costs, the time it takes to implement new functionality, and deploy new infrastructure quickly. Modular design techniques and container-based solutions are the answer. Let's explore what these are. Let's come back around to the complexity problem in a software development and deployment scenario. Like most problems, when we look for a solution, it is always better to look at other similar problems already solved by people before us. A very apt analogy for the problem can be drawn using the shipping industry. For centuries, humanity has had to ship stuff all over the world. This stuff came in various sizes, shapes, containers, and characteristics. The shipping industry had to figure out how these goods could be handled. What kind of truck could be used to haul them into the shipyard? What kind of cranes could be used to load them into the ship, etc., etc. The process of shipping our goods was tightly coupled with the goods to be shipped. Each provider of goods and the shipper needed to have specialized personnel and equipment to handle and store the goods. They needed to maintain all the expertise and infrastructure ready to go. So it made for very brittle, expensive, and cumbersome process. Representing this concern in the matrix, we can see that the situation resulted in a similar matrix of compatibility. Possible types of product to be shipped multiplied by the possible mode of transportation or shipping, with an ultimate goal of making goods reach their destination safe and intact. Some 50 years ago, someone had a brilliant idea, a container, called the intermodal container. The shipping industry standardized the size, the weight, shape, dimensions, doors, locks, mechanisms, and identification features for the containers. I'm pretty sure we have all seen a lot of them in our lifetimes. With these standard containers, we can ship anything to any corner of the world. Any size, any shape, you name it. Not only can you ship them conveniently and safely, you can stack them and ship them in a very efficient manner. And all of those different goods can be shipped at the same time. Not only that, the trucks and cranes needed to handle and transport these containers were also standardized, so no special equipment or expertise was required to handle different types of products. Now all of a sudden, we have a separation of concerns. So this separation of concerns brought about efficiency and automation, and it ended up changing the world economy, because it is so much cheaper and reliable to ship things with containers. So if you are shipping coffee beans, then your only problem is to make sure that coffee beans fit snugly inside a container. You just fill up the container with coffee beans, lock and seal it securely. Then the shipper, using a standard equipment, will be able to take it from your warehouse, ship it, and deliver it to your customer on the other end of the world. You just need to choose a standard shipper who knows how to handle these standardized containers. Therefore, you are not bound to one specialized shipper. Not only that, the future infrastructure providers and shippers can design their equipment based on this agreed upon container, and it will be all compatible. No one will need to rejig their system to handle any type of goods. So it is future proof as well. You can focus on building faster and better infrastructure like better roads, faster ships, more efficient trucks, rather than worrying about the compatibility issues. So we basically went from this chaotic way of shipping products to this more organized, efficient, reliable, and faster way of shipping products. So much so, this new method of shipping goods changed the world economy forever. Today, most cargo around the world is shipped in standard containers. Containers have brought about an enormous cost savings in shipping and logistics cost. Today, 5,000 ships deliver over 200 million containers per year. We can look around the room and we can quickly count the things which will not be in our rooms, our houses, if they were not shipped from other parts of the world. So the container solution solved the shipping problem and solved it really well. Coming back to our original problem, the goal here is to solve our compatibility matrix by moving away from the physical or virtual hardware. We can learn from the shipping analogy and solution and do the same thing for software as well. So just as we moved slowly away from physical servers to virtual servers, we start moving closer to these tiny little software containers which can contain all our code and can deploy it directly to our target environments in the exact same configuration as it ran in our development workstations. Let's take help of another analogy to understand use of containers on software development and deployment.